네, 여러분. 네, 여러분 안녕하세요. 네, 물리화학 수업을 시작해 보도록 하겠습니다. 일단은 지난 시간까지 저희가 비주얼 이퀘이션, 그러니까 이상기체 상태 방정식에 대해서 배우고 추가적으로 저희가 리얼 가스에 관련된 일단 식들, 특히나 이제 비주얼, 컨퍼레션 팩터 같은 게 저희가 배웠었고요. 그리고 비주얼 이퀘이션, 비주얼 코에피션트라는 것들도 배웠었죠. 그러니까 이제 이 비주얼 이퀘이션에서는 이제 사실 비주얼 코에피션트라는 것이 중요했었고, 그러니까 그게 이제 크리티컬한 포인트였고, 그것들을 제가 고려했을 때 리얼 가스의 상태 방정식을 구할 수가 있다는 거를 저희가 배웠습니다. 그래서 이번 시간에는 이제 반데르발스 이퀘이션이라는 것에 대해서 설명을 드리도록, 그러니까 같이 한번 이야기를 나눠보도록 하겠습니다. Okay, so let's start this today classes. So as I told you, until the last week, we have discussed about the state equation of perfect gases, and also we also discussed about the state equation of the real gases, which is the barrier equation. And then we talked about the coefficient, I mean the barrier coefficient are the important factor to consider about this state of real gases. And then today we will talk about this another state of equation which called as this can say the van der Waals equation. So I think this is a quite famous guy. This is the person who got the Nobel Prize because he developed this equation which expressed this about this state of real gases. Actually, the barrier gas, I mean the barrier the equation we have learned in the previous the classes is quite well described about this state of real gases. If we have the exact value of a barrier coefficient, but the van der Waals equation is relatively low when you compare to this barrier equation, but this is quite I mean, this becomes quite general forms of state of general forms that can describe this state of real gases because it consider some kind of some how can I say some generalized factors for the real gases. So that's why the as I told you, I mean there are the thing is that there are a couple of equations to explain about that kind of state of real gases, and one of the representative equation was the barrier equation we have learned in the last week, and the van der Waals equation is one of the kind of equation that describe about this real gas state. And this van der Waals equation, but has some kind of a more generalized forms, so it can be applied some more simplified situations. So that's why this is the one of the other types of equation to explain about the real gases. And so the important thing is that there are also the other types of equation too, but these two, one is the barrier equation and van der Waals equation. The other is van der Waals equation are the most widely used things for the real gases. So anyway, this guy won this Nobel Prize by developing this equation in theory. So that's why we need to know this kind of the equation. So what is the key point? The key point of this chapter is the Van der Waals equation is a model equation of state for real gases, like a BR equation. And this is expressed in terms of two parameters, one corresponding to the molecular attraction and the other to this molecular repulsion. So in this the Van der Waals equation, we will consider about this force attracting to these two molecules in the gases, and also we will consider together about this repulsion forces. Repulsion forces of these two molecules in the gases. Okay, so that is the key point first. And the other thing is this Van der Waals equation captures the general picture of the behavior of real gases, including their critical behavior. So we have learned about this critical points, which is the critical temperature or critical pressure or critical volume, where that kind of the state of gases, that state of substances that changes. Anyway, the kind of critical point can be explained about this kind of Van der Waals equation too. What I mean is the Van der Waals equation is the expression the explaining about the kind of the critical behavior of the real gases. So that is the other point of this Van der Waals equation we will learn here. And also the last point of this Van der Waals equation is the properties of real gases are coordinated by expressing their equation of state in terms of reduced variable. So in this chapter, first we will discuss about this Van der Waals equation first. Then we will make the other forms of this Van der Waals equation by using the kind of reduced variables. So this is kind of some transformation of the equation to some more simplified forms, or to explain about some kind of the other factors of real gases using the same meaning of the equation. So anyway, the such things are the key point of this Van der Waals equation. So we will talk about the things in this classes. Okay, so let's talk about this formulation of the Van der Waals equation. So actually, what I mean is I will not do the kind of the driving process of this Van der Waals equation, because this is quite, how can I say, so it's not quite necessary for this, but we can just have to know what is the Van der Waals equation. So this is the forms of this Van der Waals equation. So Van der Waals equation can be written as the pressure is equal to, I hope you will also write at least one time about this Van der Waals equation. It's the pressure is the volume N B over N R T minus A V square and N square. So this is a pressure, and this is volume, and you know this is the number of molecules, and this is the R and temperature and volume and N. So this is the first is shown term in this van der Waals equation. So what is it? So the A indicate this van der Waals coefficient represent the strength of attractive interaction. So this A is the coefficient about this attractive interaction. And this B is a coefficient indicate the repulsive interaction of molecules between the molecule in the gases. So as I told you, this van der Waals equation is model expressed about this these two parameters, the attraction and this repulsion. So actually, the this chapter 1 could be quite not so, how can I say, was not familiar. Is not so familiar with you guys, because the most of this equation is how can I say, the actually every equation could be one chapter of this actually physical chemistry, but we will not do this all this kind of details of this equation. But we will only, how can I say, browse the kind of physical meaning of this equation and some kind of important factor of that the equation. So that's why you don't need to so worry about this how this kind of van der Waals equation is derived. So which is the starting point of this van der Waals equation? So that kind of thing is not so be necessary for these classes, but you can just have to know what is the meaning of this van der Waals equation, and then which the critical component is the use for this kind of equation. So what they are saying using this kind of equation. So what can we understand by using this equation? So such things you have to know through this classes, not that the kind of mathematical the steps to derive the equation. So that in that point, the thing is that the van der Waals equation is the mainly the how can I say, the model about this attractive and repulsive the interaction of the molecules. So for more kind of molar form of this equation can be written as these things, because the we learned about this Vn molar volume is the N over V. Then we can simply put this value no. Simply, so V equal N Vn. So we can simply put this value here, here. Then we finally have this thing. Vm minus B R T minus Vm square A equal P. So this is the most general form of the van der Waals equation. So unless you need to remember this form of this equation. So this is the van der Waals equation. So now we understand about this. So how can write this van der Waals equation, and then which component is included, which components are included in this van der Waals equation, and what are the most important coefficients used to explain this van der Waals equation. So such things we now understand. So actually, we don't need to memorize all this kind of van der Waals coefficient, because if we have to solve some the problem using this van der Waals equation, we can simply find the kind of the coefficient value. Because we already have some kind of a database for the most of the materials we are using. So if we want to solve some kind of problem about this van der Waals equation, then we can simply, what can I say, find out the value from that database. So this is kind of example. So we have this kind of how can I say? What's the problem? Okay, so this is the, how can I say, this is the examples of the van der Waals coefficient. Sorry, what's the problem? Okay, so this is the examples of van der Waals coefficient. So the unit of this van der Waals coefficient is the ATM, the M6, decimeter 6 of molar ratio, so -2. And this is the coefficient B is this kind of a unit. So the argon has the interaction coefficient is the 1.337, and the repulsive coefficient is 3.2, and carbon dioxide has the 3.6 for A, and this the 4.29 for B. So helium and xenon has the kind of value. So as I told you, so we already have this kind of a database. So yeah, so we can simply use this kind of database for solving our problem. Okay, so as I told you, there are a couple of the state of equation to explain about some kind of gas state. So the first we know this perfect gases. This is the P equal Vm of RT. Actually, this is from the PV equal nRT. So now we learned about this van der Waals equation, and we will learn about how we will form this reduced form 2. And so there is also Barcelot and also the artery equation, but we will not cover these two things not in this classes, but we just I just want to give some example, and we know this BUR equation. So we have these two things. Okay, so this is the point. Okay, so now I want to solve one examples with you. So this is example. So using this van der Waals equation to estimate a molar volume of carbon dioxide at 500 K and 100 atm by treating it as van der Waals gases. So let's solve this problems. I will give you a few minutes, and then let's solve together until you have some time. Just think about it. How can you solve this equation? Okay, so I hope you guys just pause this movie clip and then have some time to solve this solution, this examples, and then continue this the movie clip again to see how this solve this question. Okay, so let's solve together. Okay, so as explained in this example, so we will use this van der Waals equation. So what is the van der Waals equation? The P core is the V minus NP. Sorry, it's not the things. Okay, so this is the. Okay, so the P equal VM sync P equal VM minus B over RT and minus VM square A. So this is the van der Waals equation. So to find the expression for this molar volume by solving this van der Waals equation, we need to multiply this both sides with this Vm minus B Vm square. So then we can simply multiply this term and this term with this equation. Then we have Vm minus B Vm square P and RT, these things, RT Vm square, and the term is the minus Vm minus B A. So, and then we will make this thing as your the how can I say the original equation about this Vm by dividing this term with the P. So then just simply dividing these two point by this P, then we have Vm minus B Vm square and P over RT Vm A. Then I will rearrange this equation. Vm minus B over Vm square minus P분의 RT Vm square minus Vm minus B A. And by this is this sorry, this is equal 0. So by rearranging this equation with this Vm, then finally we have this form Vm 3 and B plus P RT Vm square plus P over A Vm minus P A B equal 0. So if we solve these terms, then we will get this coefficient. So yes, actually, if we try to solve this equation, but I'd like to use some kind of software to solve this thing, because this is not the mathematical process. So actually, this is also quite complicated. So I hope so. We don't need to solve this thing here, but if you want to solve these things, then you can simply use some kind of software solving this equation. So anyway, so the to solve these things, we have to know what is the B and A. Then so actually we wanna know this coefficient P over R T plus B, this one, and P over A and P over AP. So if we know this value, then we will have some kind of equation about this volume, because we know this temperature and this pressure, and this B and A is the coefficient about this carbon dioxide, and this coefficient can be shown in this table. So for carbon dioxide, the coefficient A is the 3.6, and coefficient B is the 4.29. So you can simply use the value. So I just written it, the A equal for carbon dioxide is the 3.61 and B equal 4.29. And if we apply this value here, and then apply to this also temperature and pressure, then we get this thing as 0.453 the decimeter 3 per mole. And for this also 3.61. So this is the 118, and this is this one 8. So we have this value. So this one. And this is also can be solved by applying this values here, and then we have 1.55, 10 to minus 3, and decimeter 3, and more here. So by simply applying all this value to this equation, and then for more simplifying this equation, we will put this x equal VA and unit equal decimeters 3 and per mole. Then this equation can be expressed as this one is the x3 minus here, this one, 0.453 x squared plus 3.61 10 to minus square x, and then minus 1.55 10 to minus 3 equal 0. You know this value r, this is the constant, and here we use this r equal, I just saw reading the paper, H204. So now we have this kind of some kind of general forms of this equation. So if we solve this equation, then we can estimate its molar volume, the range of these molar volumes. Okay. So using some kind of structure, and then if we solve that this equation, then we have for this solution of x equals 0.366, and this means the Vm equals 0.366 decimeter 3 per mole. So so what this means? So in this condition of the temperature of 500 Kelvin and also the pressure is 118, then the molar volume of the carbon dioxide is 0.366. But if we assume that this gas is a perfect gases, then if we also calculate this molar volume, then we will have this value of 0.410. So what this means, there is some kind of the deviation from this true value between these real gases and also the perfect gases. And this is why, as we also discussed in the previous classes, this because there is attractive and also the repulsive force between the molecules in those gases, in real gases. So that kind of things is expresses the kind of deviation of the values. Okay, so you might understand how we can solve that kind of molar volume by using this van der Waals equation, and we will a little bit more discuss about these features of the equation. of the van der Waals equation. Okay, so let's think about this. So we will talk about this how this van der Waals equation so well explain about this the state of real gases. So for that we have to consider first about this van der Waals loop. So this van der Waals loop is the how can I say, this is the isom the data for the some gases, and this is the state of these gases depending on the temperature and volume and pressure. And so as you know that it's if this volume is decreased, then pressure should be increased. So this is why this graph have make this kind of forms like this or like this. But in some point, there is this kind of some unrealistic case where this pressure is increased while this volume is decreased. I'm sorry. So where the pressure is decreased like this, while this volume is still increased, still decreased. So that kind of thing is called as the van der Waals loop. So the oscillations, we call this kind of oscillation, call this van der Waals loop. So this is the the graph the drawn by this van der Waals equation. But in this graph we can find that kind of the oscillation which called as van der Waals loop. But this kind of van der Waals loop is the unrealistic because the it's not, how can I say, it's kind of a nonsense situation. So pressure volume is decreased, but the pressure also the decrease. It's not true actually. Volume decreased and pressure is increased. This is the real case, realistic case. So we have to make some kind of how can I say, the compensation process for this kind of van der Waals loops, and then we will use this kind of Maxwell construction method. Actually, you don't need to worry about this. What is the Maxwell construction actually? But we can just simply think that we can make this kind of lines for this oscillation, and the area of between this the transition point should have same in this Maxwell construction. Then we can just simply make this thing as like this. So we will I mean this area as the flat region. So this situation, this kind of a construction method is a Maxwell construction. But it's not important. So what is the Maxwell construction? But the thing is that if we use this kind of van der Waals the equation, then we can meet this kind of unrealistic situation. This is the one feature of this van der Waals equation. So to compensate this kind of unrealistic situation, we have to the reform, how can I say, kind of a reconstruction of this that kind of a situation to get this realistic value for using this van der Waals equation. So anyway, that is the one feature of this van der Waals equation. So based on the fact that there is some kind of van der Waals loop, then we will have some more principal features of this van der Waals equation. So first, the perfect gas isosomes are obtained at high temperature and large molecule in this van der Waals equation. So so kindly I provide again about this. This is the van der Waals equation. here. So what this sentence means, the perfect gas isotherms are obtained at high temperature and large volume, means this first term should be much larger than the second term. So what is mean? So at this high temperature, what is mean? This high temperature, then this RT is very much higher than this factor B. So what this mean? Because this RT becomes really high, then we can ignore the second term. Then we only have P equal B over RT. But because this RT is still really high, then we can also simply ignore this thing too. Then this will be same as the perfect gas, the state of equation, because the V can be ignored because the RT is too high. RT is too high. So in this kind of van der Waals equation, we can get this the perfect gas situation if the gases is under the really high temperature. Okay, the other case, and if there is a really large molar volume, what this means? So because what this means, this is the Vm, if Vm equal really high, okay, so if Vm equal much larger than this coefficient B, then we can simply ignore that is B value. And also because Vm is really high, then also we can ignore the second term. Then we will only have P equal Vm over RT, which is the perfect gas state of equation. So Vm. And this Vm equal NV. So then we have P V equal nRT, which is the perfect gas equation. So this is the first principle of this van der Waals equation. So perfect gases isotherms are obtained at high temperature and high molar volumes in this van der Waals equation. So this is the one feature. And second feature of this van der Waals equation is the liquids and gases can coexist when cohesive and dispersive effects are in balance. This means. So if this first term and the second term is same, so what this means, the this is the kind of factor by this the dispersing effect, and this is a factor by the cohesive effect. So if this dispersing cohesive effect in balance, then in this van der Waals equation, these liquid and gases can be coexistent. So this is the other principle of this van der Waals equation. And third thing is the critical constant are, so what is the kind of a TC or VC or PC related to this van der Waals coefficient, which is the A or B. So what is it? So this extra converge as if T approach to this TC, which is a coincided T called TC, and the critical point, the curve has a flat inflection like this. So what this means? So in this van der Waals equation, we learned that there is the oscillation, and we will make this kind of a flat region, which is the called this TC, where the temperature is approached to this TC, then there is some flat region. And this flat region can be explained as this kind of the deviation process. So the slope, because this slope will be 0, and also acceleration for this also become 0, then we can have this VC value and PC value and TC value about this coefficient of van der Waals. So actually, you don't need to too deeply think about this kind of system. But at this point, we can get this kind of critical value, which can be correlated to this van der Waals coefficient. This is just kind of a process, but simply what we want to know about this picture 3 is the kind of critical value can be explained about this coefficient of this van der Waals coefficient. And in this regard, we can also explain about this critical compression factor as this that C equal RTC over PC and VC. This is derived from like this one. So we know this one. Then that equal RT over PVM. But for this kind of critical point of this van der Waals equation, and then we have this critical compression factor. Okay, so now we know what is the van der Waals forces, and also what is the how can I say the principal features which are involved in this van der Waals equation. And then lastly, we'll talk about this how can we transform this van der Waals equation for more like the general forms. So we can call this as a principle of corresponding state. So the critical constant in this corresponding state, principle of corresponding state, the critical components are characteristic property of gases. So what this means? This TC, VC, and PC, the state of gases is the transient. So we can use this thing as a yardstick for explaining about this gas system. So it may be that a scale can be set up by using them as a yardstick. So we can explain about the state of these gases by using this TC, VC, or PC values. So we want to use this kind of value for the state of equation. For example, the van der Waals equation, such as van der Waals equation. So we will use define this reduced variables with this critical point. So reduce the variable volume will be defined. This is just a definition. Defined as the VC over Vm, and reduced variable PR equal PC over P, and reduced variable TR equal TC over T. So if we have this kind of reduced variable, then we can transform the van der Waals equation to the reduced variables system. So let's see how we can do that. Okay, so again, we will start with this van der Waals equation. So P equal Vm minus B over RT minus Vm square A. And then we will reorganize it with this reduced variable. Say VR equal VC over Vm, PR equal PC over P, TR equal TC over T. Then we can simply apply this thing to this equation. Then we have this PRPC equal VRVC minus B, RTRTC minus VR square, VC square, and over A. And also, we also talk about this critical value, which is related to this the van der Waals coefficient. This one. So let's see. We use this value. Then simply we put this value, all this thing here. Then we have this kind of the equation. And if we arrange this equation for this reduced value, then finally we have this equation. So we call this as the van der Waals equation for the reduced variable system. So this is the PR equal 3VR minus 1 over 8R minus VR square over 3. So physical meaning of this equation. So we can think about this some kind of reduced system according to this critical point. So what this means? So actually, in this the original van der Waals equation have this coefficient. So to understand about this van der Waals equation, we have to know this van der Waals coefficient. So that was the point for this original point. But here, so what is the difference? There are no van der Waals coefficient, but there are only VR, TR, PR, the reduced value of this equation. So what this means? So if we know this kind of critical point, then we can oppositely derive this coefficient of A and B. So what this means? So if you need this kind of only just A and B coefficient, van der Waals coefficient, then you can simply use this equation. but you don't need this coefficient of A and B, but you know, so you but in some cases you can find the kind of critical the point of the gases by I mean the experimentally. Then we know that values, but then you can simply recalculate this A or B or Van der Waals coefficient using the critical value by using this Van der Waals equation. So that's why we just derive this kind of reduced form, which the basically corresponding to this original the equations. So this is the concept of this Van der Waals equation. So actually, this is the end of this chapter 1. Actually, so chapter 1 is the about this some kind of basic the part of the gases, the physical meaning of the gases. So from this chapter 2, we will more like learn about the, some kind of the theory of heat. Anyway, so here we just focus on the gases. So this is a roadmap chapter 1. So if we have these gases, then we can have some kind of compression factor. We can simply think about this. The gas is a perfect yes or no. So if yes, then we can simply use this perfect gas equation. And at this constant n and temperature, then we will have this Boyle's law, right? And if there is the constant n and p or the constant n and v, then this equation is the Charles law. The combination of this Boyle's law and Charles law explain about this state of equation for perfect gases. And at this point, we also know about this the molar volume, which is the P over RT. Which is the N over V. So this is what we know. And if the gas is the not the perfect gases, then we have to use some kind of state of equation for the real gases. The first thing we know this BUI equation, which can be expressed as the PVM RT1 like this. And this the coefficient is important for this BUI equation. So this kind of coefficients called this the BUI coefficient. So to solve this BUI equation, it's important to know about this exact value of this BUI coefficient. So that was the point of this BUI equation. And the other type we also know in the chapter 1 is the Van der Waals equation. So this is the Van der Waals equation. So we know this P equal Vm minus B over RT minus Vm square over A. And this B and A is the Van der Waals coefficient. And if we know this critical value, and this, how can I say, one of the points of this Van der Waals equation is the critical point can be expressed as the with the correlation of this Van der Waals coefficient like this. Then using this critical constants, we can make this reduced variables. Which can express about some type of different types of Van der Waals equation. So what this means, actually, I didn't talk about these things. So I just say this, the critical compression factor is the ZC over RT, TC over PC, VC, and this is the known to be approached to this 8 over 3. So that is the what I saying about these things. But we don't want to talk too much about this thing as well. But anyway, so we also know this critical compression factors. So actually, so this is actually all for this chapter 1 actually. So if we understand this roadmap, then yeah, so you can understand about this gases too, state of equation of gases too. Okay, so I think we'd better stop here at this point, and before the finishing this class, I will give you a quick summary in Korean, and then stop this classes. 네, 네, 정리를 좀 한국말로 해드리고, 챕터 1이 이제 끝났습니다. 그래서, 마지막으로 한번 간단하게만 정리를 좀 해드리고, 오늘 수업을 마무리하도록 하겠습니다. 그러니까 이 기체의 상태 방정식에서 일단 여러분이 첫 번째로 우리가 접했던 게 바로 퍼펙트 가스, 그러니까 이상기체라고 우리가 기체를 가정했을 때 퍼펙트 가스에 대해서 우리가 기체 상태 방정식을 얘기를 했었고, 그 다음에 우리가 이게 이제 기체가 안에서 분자들끼리의 그 인터랙션이 발생하다 보니까 실제 기체의 어떠한 그 상태가 이상기체 상태 방정식으로 완전하게 표현이 되지 않고 있죠. 그래서 새로운 상태 방정식으로 이제 실제 리얼 가스에 대한 상태 방정식이 필요했기 때문에 이런 비리얼 이퀘이션이라든가 오늘 배운 이런 반델바스 이퀘이션이 이제 설명이 된 거죠. 그러니까 이전 시간에 배웠던 비리얼 이퀘이션이랑 오늘 배운 반델바스 이퀘이션이 뭐 완전히 뭐 다른 거라기보다는 리얼 가스의 상태를 설명하기 위해서 다양한 사람들이, 그러니까 이게 무슨 말이냐면 어떤 리얼 가스에서 완벽하게 뭔가 딱 정립된 그런 모델이 있다기보다는 서로 다른 어떠한 가정과 어떤 접근법을 통해서 그 리얼 가스의 상태가 이렇게 될 거다는 거를 모델로 만든 어떤 대표적인 두 개의 이퀘이션을 우리가 지금 배우고 있는 거죠. 배웠던 거죠. 하나는 비리얼 이퀘이션이고 하나는 반델바스 이퀘이션. 이제 비리얼 이퀘이션 같은 경우에는 그 코에피션트 값을 정확하게 아는 게 굉장히 중요해요. 비리얼 코에피션트라는 거를. 그래서 우리가 그거를 잘 모르면 비리얼 이퀘이션은 어떤 푸는 데 있어서 조금 지장이 있을 수 있고. 근데 반데르바스 이퀘이션은 조금 더 심플리파이 된 그 형태이긴 합니다. 네. 그래서 반데르바스라는 사람이 요걸 가지고 노벨상 탔다고 해요. 그래서 이제 중요한 거는 뭐 이런 것들을 이제 저희가 배웠었고 포인트를 배웠었고 이 반데르발스에서는 요 어트랙션과 리펄션에 대한 어떤 그 코에피션트 팩터를 우리가 이 그 상태 방정식에 녹여낸 게 바로 이 반데르발스 이퀘이션이었고, 그리고 특히나 이 반데르발스 이퀘이션에서 또 한 가지 중요하게 작용하는 것이 바로 이 크리티컬 비헤이비어, 그러니까 이 TC, VC, 뭐 PC 같은 크리티컬 포인트들에 대해서 반델바스 이퀘이션이 또 잘 설명을 해주고 있습니다. 그런 것들이 있다는 거 먼저 아시면 될 것 같고, 기본적으로 반델바스 이퀘이션이 이렇게 표현이 되죠. 실제로 많이 쓰는 게 이 폼이죠. 몰라 볼륨에 대해서 왜냐하면 더 보이기도 쉽고 나중에 이렇게 어떻게 실제적으로 더 많이 사용되는 게 몰라 볼륨이기 때문에 이렇게 많이 쓰이고, 여기서 중요한 게 A가 그 attractive interaction을 나타낸 코에피션트고, 그리고 이 B는 그 repulsive interaction strength를 나타내는 코에피션트죠. 그래서 대부분의 그 잘 알려진 가스들에서는 이 A 값과 B 값이 데이터베이스가 다 돼 있어요. 그래서 여러분이 뭐 A 값을 구하고 B 값을 굳이 어떻게 뭐 수학적으로 계산할 필요는 없지만 뭐 그렇게 계산할 수 있는 방법도 있다는 걸 이제 마지막에 말씀을 드리긴 했었죠. 그래서 어쨌든 이런 값들이 있다. 뭐 그냥 하나만 보시면 뭐 그 카본 다이옥사이드, 그러니까 이산화탄소 같은 경우에는 지금 뭐 리펄시브랑 뭐 어트랙티브 포스가 좀 큰 편이죠. 헬륨 같은 경우에는 어트랙티브 포스는 굉장히 작고 리펄시브는 굉장히 크죠. 그러니까 비교적으로 요거에 비해서 그럼 리펄시브가 굉장히 많이 작용을 하겠죠. 뭐 이런 게 있다. 그래서 뭐 그냥 몇 가지 상태 방정식을 쭉 나열한 거예요. 예를 들어서 퍼펙트 S가 있었고 BDR 이퀘이션 배웠고 반데르발스 이퀘이션 지금 배웠고 뭐 이런 것들도 있습니다. 뭐 다른 사람들이 뭐 이렇게 몇 가지 더 설명한 것들인데 요거는 이제 저희가 다루지는 않았고요. 예를 들어 이런 것도 있다. 이런 거 이렇게 말씀을 드린 거였고 그래서 반데르발스 이퀘이션을 가지고 뭐 간단한 예시 한번 풀어봤었고요. 근데 이제 이 반데르발스 이퀘이션에서 보면은 반데르발스 루프라는 게 발생합니다. 그러니까 이 크리티컬 포인트에서 이런 식으로 오실레이션이 이제 발생을 하는 거예요. 이 오실레이션이 뭐냐면, 그러니까 TPV에 대한 그래프를 봤을 때 오실레이션이 발생을 하는데, 이게 지금 보시는 것처럼 부피가 감소를 하면 당연히 압력이 감소를 해야겠죠. 네, 부피가 감소하면 압력이 증가를 해야겠죠. 그렇죠? 이렇게 작아지는 압력이 커지면 부피가 감소하고 하면은 압력이 작아지고. 근데 부피가 작아지는데 압력도 줄어들어요. 이거는 어 그 그러니까 unrealistic한 그러니까 실질적으로 발생하기가 어려운 그런 넌센스한 시츄에이션이라는 거죠. 그래서 사람들이 이 오실레이션 포인트에서 이런 웩스웰 컨스트럭션이라는 수학적 가정법을 써가지고 여기다 라인을 쫙 꺼요. 쫙 꺼서 위와 아래의 면적이 동일하게 지는 라인을 쫙 꺼가지고 여기를 플랫하게 만들어 버립니다. 이게 맥스웰 컨스트럭션이고 이렇게 했을 때 이렇게 해서 표현을 하면은 뭐 크리티컬 포인트를 표현해 줄 수 있다. 뭐 이런 정도로만 알고 가시면 될 것 같고 사실 정말 중요한 건 요쪽이에요. 요즘 뭐 앞에 거는 뭐 그냥 그런 것만 있다 하는 거 보시면 되고 여기가 이제 여러분이 중요하게 보셔야 될 것 같은데 여기서 퍼펙트 게스 이 반데르발스 이퀘이션에서 그쵸 퍼펙트 게스가 될 수 있는 상황을 설명을 하죠. 언제죠? 하이 템퍼러처 온도가 굉장히 높으면 요 반데르발스 이퀘이션에서 RT 요 텀이 굉장히 커지기 때문에 나머지를 우리가 다 무시할 수가 있게 되는 거죠. 네. 그렇게 하면은 뭐 P equal RT가 되는 거고 이게 결국은 그 뭐냐 퍼펙트 S 상태 방정식하고 같은 텀이 되는 거죠. 근데 반대로 볼륨이 아주 크면 볼륨이 아주 커서 네. 여기가 아주 커지면 지금 요 텀은 이제 또 무시가 되는 거죠. 네. 요 텀 무시가 되죠. 그러면 남는 거는 P equal VRT가 되죠. 왜냐하면 V가 P에 비해서도 굉장히 크기 때문에 P도 그냥 없는 셈 칠 수 있는 거죠. 그러면은 이것만 남고 그래서 이게 이상기체 상태 방정식을 수정한다. 그러니까 이런 조건이 있고 두 번째는 요 첫 번째 텀과 두 번째 텀이 같은 경우 그러니까 이게 무슨 말이냐면 첫 번째 텀은 코에피션트 B에 대한 텀이잖아요. 그러니까 코에피션트 B는 지금 얘기하고 있는 게 그 리펄시브 그러니까 결국 여기서 디스퍼싱이라는 거예요. 디스퍼싱이 이제 이렇게 벌어지는 거니까. 그리고 A는 이제 어트랙티브잖아요. 그래서 코에시브에 관련된 내용이. 그래서 디스퍼싱과 코에시브에 관련된 그런 그 효과를 밸런스에 맞춰서 이렇게 두게 되면은 리퀴드와 가스가 공존할 수 있는 상태가 된다. 반델발스에서. 그러니까 이게 늘어나는 것과 줄어드는 게 그러니까 몰레큘이 늘어나고 줄어드는 게 이게 밸런스 있는 상태인 경우는 결국은 가스도 될 수 있고 리퀴드도 될 수 있고 약간 뭐 그런 상태라고 생각을 하시면 돼요. 반데르발스 이퀘이션에서 설명하는 그렇게 되는 거고 그리고 그 그 세 번째로는 뭐죠? 이 반데르발스의 코에피션트들 A랑 B가 결국은 이 크리티컬 어떤 템퍼러처, 그러니까 크리티컬 이 포인트들하고 연관해서 나타낼 수 있다. 그러니까 이게 뭐냐면 이게 오실레이션이 발생을 하는데 오실레이션이 발생하는 데서 여기서 TC로 이렇게 가까워지게 되면은 이게 요 지점에서 A랑 B로 설명이 될 수 있다. 뭐 이런 얘기인데 뭐 이렇게 뭐 여러분이 아실 거보다는 이게 어쨌든 간에 반데르발스 코에피션트는 이 크리티컬 포인트하고 이런 식으로 어쨌든 관계를 가지고 설명이 될 수 있다. 요까지만 아시면 되고요. 그래서 요거를 여러분이 아시고 나고 뭐 마찬가지로 컴프레션 팩터도 크리티컬 포인트로 우리가 나타낼 수 있다. 요거까지만 아시면 될 것 같고요. 이거 결국 여러분이 이제 중요하게 아셔야 되는 게 요 세 번째 걸 설명하는 거는 결국은 얘기 드리는 거는 요거를 풀기 위해서 이제 설명을 드립니다. 그러니까 이게 TC나 VC나 PC가 일종의 하나의 척도가 될 수 있다. 가스의 상태를 나타내줄 수 있는 척도가 될 수 있고, 그래서 그 이 가스의 상태를 나타내는 척도를 만들기 위해서 이런 식으로 새로운 폼, 리듀스 베리어블이라는 걸로 우리가 표현을 해준다. 왜냐면 이게 일종의 하나의 크리티컬 어떠한 스탠다드 포인트라고 생각을 하게 되면은 이 스탠다드 포인트 대비의 어떤 변화율이라고 하는 걸 나타내면은 이런 리듀스 베리어블이 되는 거고 VR, PR, TR 이런 게 되는 거고 요거를 사용하면은 이런 식으로 반데르발스 이퀘이션에 대해서 요거를 넣어주고 아까 이 크리티컬 컨스트레인트 관련이 있다. 그래서 요게 이렇게 넣어주면 궁극적으로 어떠한 새로운 형태의 반데르발스 이퀘이션을 우리가 얻어낼 수가 있는데 이게 뭐 다른 건 아니죠. 요거랑 요게 뭐 서로 다르다는 건 아니고 결국은 똑같은 건데 이렇게 좀 다른 형태로 나타낼 수 있다. 근데 여기서 큰 차이점은 뭐냐면 오리지널 원래의 반데르발스 이퀘이션은 요 A와 B가 이런 식으로 존재를 하죠. A와 B가 존재를 하는데 지금 이제 변환된 reduced variable 활용한 거는 A랑 B가 없는. 그러니까 아까 뭐 요런 걸 얘기해 준 게 결국은 A랑 B가 없는 요식을 우리가 만들 수 있다. 이런 거를 여러분이 이제 알 수 있다. 이런 거를 말씀드린 겁니다. 그래서 원래는 A랑 B를 알아야 우리가 요 반데르발스 이퀘이션을 풀 수가 있는데 여기에서는 A랑 B를 몰라도 반데르발스 이퀘이션을 풀 수가 있고 반대로 요거를 통해서 A랑 B를 역으로 계산을 해줄 수가 있다. 그러니까 우리가 뭐 TC, VC, 뭐 PC 이런 거를 실험적으로 뭐 알게 되면은 요거를 가지고 이런 PR을 계산을 해줄 수, 요 코에피션트도 계산해 줄 수 있다. 뭐 이런 의미가 되는 거고요. 자세한 건 제가 앞서 다 설명드렸죠. 그래서 최종적으로 요 로드맵을 통해서 챕터 1을 마무리를 하게 됐습니다. 챕터 1에서는 여러분이 이제 결국은 이 컴프레션 팩터 이 가스를 우리가 지금까지 배웠는데 가스의 상태 방정식 가스를 딱 두고 봤을 때 가스가 퍼펙트하냐 yes or no 그래서 퍼펙트하다 퍼펙트했다 그러면은 이상기체의 상태 방정식 사용하면 되는 거고요. 그리고 n이랑 t가 일정할 때 보일의 법칙을 따르고 p나 v가 일정할 때는 샤랄의 법칙을 따르는 거죠. 요게 결합돼서 요게 된 거니까. 그리고 뭐 이런 것들 부수적인 것들은 뭐 설명을 드린 거니까. 근데 퍼펙트 엑스가 아닐 경우에는 우리가 두 개를 배웠죠. 비주얼 이퀘이션이랑 반데르발스 이퀘이션을 배웠죠. 두 개에 대해서. 여기서는 비주얼 코에피션트라는 게 중요하다. 여기서는 반데르발스 코에피션트가 중요하다. 근데 뭐 크리티컬 포인트하고 이런 식으로 반데르발스 코에피션트는 관련지어서 설명이 가능하다는 것까지 여러분하고 이야기를 했었습니다. 네, 이렇게 했었죠. 네, 이렇게 했었습니다. 네, 그래서 아무쪼록 일단 챕터 1은 이렇게 마무리를 하고요. 네, 다음 시간부터는 이제 인력학 제1, 2법칙 이런 것들에 대해서 좀 배워보도록 하겠습니다. 네, 여러분 고생하셨고요. 다음 시간에 또 뵙도록 할게요. 수고하셨습니다.